Time for another DraftScience video presentation. Yeah. Alright, some more stuff on photons, videos by presenters of science, and, some obvious flaws. Said that word obvious a lot. Let's just say, apparent. You can't miss them if you really analyze it. Nobody really did, and that's the point. Nobody spent any time really picking at photons to try to figure out what one is, I guess. These are simple experiments, and if you did the experiments and you tried to make the theory, the math, fit the results you got, you'd find out that no, it just doesn't work, and that you have to change the theory, change how you derive your variables to get the right answer, and they never did that. And they had hundreds of years to do it, and they didn't do it. At least 200. For 200 years, it's been really, any real deliberate effort to study a photon would have noticed that what they're saying happens isn't true. That, like I said, the math just didn't work. I'm specifically pointing to the Young diagram, the one they use as a solid experiment, and nobody bothered to see that it ain't so solid. I think they, to some extent, did bother because, again, they did change their vernacular, the way they talked about the experiment, talked about having infinitesimally small slits, or infinitesimally small impediment, and that qualification was a concession that it doesn't work otherwise. It's not a good theory otherwise. And again, so it's sort of just like the idea of ignoring the fact that the single slit produces an interference pattern and instead calling it a diffraction pattern, when clearly it's not just light spreading, it's light, creating bands of light. So it was all there in pieces. I could argue 10 years ago I could have pointed it out that something's wrong, but now I can point out exactly what's wrong. Well, more specifically what's wrong.
Welcome to the second video in this series on quantum mechanics. In the first video, we saw that classical physics failed to explain the relationship between temperature and electromagnetic radiation, such as arises in an incandescent light bulb.
Right. So this is the this same old classical physics argument that we really have to accept some sort of new way of thinking, that this isn't just about momentum, and all it is, it's just about things interacting with things, and there's if the thing has momentum, it conveys its momentum. There's an implication. Two things interact, and the two things end up leaving with pieces of each other's identity stuck to them, in terms of their future path will now be changed because of the interaction, and that there's some notion that there's a conservation of their movement in the byproduct of their interaction. And those simple principles don't have to be destroyed. No.
The classical prediction is that radiation...
So again, they call it a classical prediction. Nobody predicted it. Nobody stated it. Nobody defended it. Nobody said, I know that there's a straight linear line that has to do with energy distribution. No, nobody argued any of this. So this is just a straw man they create to argue that somehow the classical physics just didn't work and blah, 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 when nobody argued for this straight line. They just didn't. And the idea of what energy is the only thing that changes. The only reason why these lines have to diverge is because we define energy as something we see as energy. The fact is, the total energy, that is the amount of heat and other byproducts that you'll create, is a straight line. Okay, it's just that some of the energy is more noticeable to us because it makes the turbine spin in the right direction. Right? I can put energy I can put electricity into a motor in a form where all it'll do is get hot. Okay, nothing else will happen. It won't accomplish any work. And so therefore somebody could say, oh, it lacks energy. No, it lacks constructive energy. It lacks you applying the energy in a way that creates a linear movement. You know, back and forth seems quite useless for a lot of projects. Now, some it works, you know, air pressure, compressor, or some other thing. But generally speaking, this kind of motion, go to point A, go to point B, go back and forth, isn't going to get you very far. I mean, we want to see something move, you know, get somewhere. And so that's all this is about, is you could say that somebody who's exercising by walking 2 steps forward and walking 2 steps backward, you know, you'd say, well, he only moved 2 feet. And therefore, if I do an energy equation, he didn't accomplish anything and he didn't do any work. Well, he obviously did. You're just interpreting it based on one standard that doesn't really have anything to do with real energy. So all of this is just, it's just the part of, you know, it's now just propaganda. It doesn't really have anything to do with being a scientist. This using these terms like classical physics.
Intensity will always increase with frequency. Planck was able.
So again, it'll always increase with frequency. Again, nobody, there was no reason for anybody to have that kind of perception, beyond the fact that obviously anybody who knows the word frequency and understands what it means understands that, well, if I shoot 7 bullets in 1 second versus shooting 2 bullets in 1 second, that I'm going to affect the world a lot more with the 7 bullets than with 2 bullets.
To derive a radiation law that matches what is observed. Intensity reaches a peak at a certain frequency and then rapidly drops off at higher frequencies. But to achieve this, Planck had to assume...
So again, it's the intensity they're measuring based on the number of photons versus this idea of how much the photon... And it's really just about effects. And if you take out effects, the fact that constructive application of a force versus, again, where you're constantly going back and forth, that's all this is about. It's as simple as that. If you understand that the total energy, that is the amount of radiation versus the amount of gamma rays you're producing versus the amount of infrared radiation you're producing, is always going to be equal to just the simple fact that the higher frequency has more elements in it. There's more energy in it because it has more elements in it.
That radiated energy comes in discrete chunks, or quanta. At frequency nu, the quantum of energy is Planck's constant h times nu.
So again, nu is they're using the word v. I don't really understand why they're doing that, but whatever. It's, you know, it doesn't make much sense to me.
This assumption an act of desperation, and although it produced the correct formula, he was highly skeptical of it. The assumption...
So that ought to be something to take into account, is that, oh, look, it works, but it doesn't really work for a good reason. That kind of argument. People should pay attention to that when it's like Eddington saying in his journal, I wouldn't stake my life on these results. You know, that should mean something.
Work because at a temperature T there's an average thermal energy, kT, available to excite a radiation mode. Here K is called Boltzmann's constant. For low frequencies, the energy quantum is much less than kT. The mode can have an energy of kT, which is the classical...
Alright, so maybe I just start drawing here just to explain some context and say, well, what all this crap boils down to. It worked, I think. Oh, we do have to move that out of the way. Okay, well, that's good. We can cover this crap down here with that. So what all this is just about is the fact that, yes, phenomenon happens because a photon, or what we call light, or radiation, isn't as simple as here's a clump of radiation. Now, it is for gravity that simple. Okay, there's just a quanta of force, and the quanta of force is used up. All right, it hits a piece of an electron or a proton, for example, and it moves it a little bit of distance. And the movement doesn't mean it reflected off and scattered or did something like that. No, it just hit it. It pushes it until an equal but opposite action happens. That is, another piece of little force hits from some other direction, and then they can both reflect. But until that happens, this piece of stuff moving the speed of light hits a dead piece of matter, an electron or proton, that may have momentum, but I mean at the time. But the point is that it doesn't have any action of its own. It had to be moved by a force previously. But the point is if it isn't moving, then the action is going to be that this thing will push it. Now, if it's already moving, then you're going to get that reflection. Okay, so if this thing is already moving towards or away from, well, towards this thing, so it has to be movement in the opposite direction, opposite force. And so if it's already moving, then this thing will just bounce off, and this will lose a piece of force in the opposite direction. So this will stop moving, theoretically, for a moment in time. So anyway, back to the first part of the story. I mean, it's not that complicated. You should be able to follow along. So this is moving the speed of light. And let's say this piece of matter, an electron or proton, is at this moment not moving anywhere. The fact is that this piece will push it. It'll hit it. It'll stay here with it. Both of them will move a distance from A to B. And so now they're moving in a direction because this thing hit it. I'll get rid of that little arrow. And they're going to move slower than C. So now it's going to be less than C that this thing is moving. So it's lost. This piece of force was going a certain place. It should be here. And it's stuck back here, still pushing this thing. Now, when the opposite piece of force hits, okay, and it inevitably will in a microsecond or whatever, what's going to happen is they'll hit just as kinetic things would do. This little bit will fly off in that direction, which is essentially this bit going that way. Right? This reflection will look like this thing just went straight through. And this will cause that to reflect. So this bit goes this way, which is essentially can be looked at as this is now liberated. Right? So now you've got both of these bits back in the free universe as each other. Okay, so it's exactly the same as if they'd gone straight through each other, but that it didn't really happen. One put the other guy's hat on, and they switched roles. And the fact is now the matter will be stationary. Okay, they'll stop moving because nobody's pushing it at this moment. And then somebody new will show up and he'll push, and then it'll move again. Now, in theory, a gamma ray or something like that can push one of these electrons, because a gamma ray would be a bunch of these little things right close to each other. And you could sort of understand that they could pile up behind, an electron. Now, they really can't because they have polarization and all these other rules, but the energy can pile up. You wouldn't necessarily call it a gamma ray, because it won't be a gamma ray until the opposite force creates it. But you could understand that now if a force hits this way, the same reflections will happen. This one will reflect off, it'll lose this piece. Then a new thing hits and it'll lose this piece. And a new thing hits and it'll lose this piece. And that's going to be a frequency that's going to be leaving this electron. So it can pile up energy in the constructive direction, but it can't pile it up in the opposite direction. So that's part of the simple mechanics. So you can add energy, that is, you can add force to an electron, okay, but you can only subtract it one piece at a time, cause the reflection. So that simple mechanics you have to pile on to understanding. So that explains why there's gravity, essentially, because the little bits of force, when electrons and protons are moving inside of an object, they're moving because they're actually interacting with force constantly. So when they're going this way and they stop and they do this and they move around, every time they move somewhere, they have absorbed a little bit of energy from the force because the force didn't go as fast while it was pushing the matter. So this push theory, push mechanics, does explain why there's gravity, because more energy goes into the Earth than gets back out because it spent a bunch of time pushing the electrons and protons. It lost time. Alright, so the photon is made of exactly the same stuff. And the subjects they never talk about are the fact that the photon has a very, very large polarization. So all the light we can see, we've never made a photon that doesn't have big polarization, a visible photon. Now, as the frequency, so obviously I'm saying frequency is going to be just particles at a distance. That's the simple explanation. Okay, so a photon is a pattern that goes through space. It's not a thing. It's not a blob. It's not a ball. A photon is made of little clumps of momentum, and the momentum isn't in perfect alignment, and that's its polarization. It was created at slightly different moments on an atomic surface, and the little bits are parallel to each other, but they're not, because they came off that surface, but, and they have a frequency, and the polarization is proportional to the frequency, and the polarization is large, just as the frequency, if you counted it in how many atoms, the frequency of visible light is 500 atoms, of distance. You could stick 500 atoms inside that wave they draw. You could put 500 atoms in there, so it's not as tiny as we know it is in terms of its energy, because we know that these little bits have a tiny amount of energy. Okay, but the trick is that tiny amount of energy, when it hits it with a pattern, will make the difference between an electron being here and an electron being here. It'll change its position. And when it changes its position, it does it at a certain speed. And the speed at which it changes that position is going to mean that it's going to interact with more of the universe. If I move my hand quickly towards you, I effectively push a bunch of light into you. Just a fact. If I moved quickly away from you, I don't push much light. I get dimmer and dimmer and dimmer. The faster I move, the dimmer I get. These are all just facts that electrons are living in too. They're in the same universe we're in. Everything's floating around in the same space. And so you have to understand that this photon's polarization is basically telling you that these little bits, all right, can't interact with one electron. The electron is almost 1,000,000 times smaller than this polarization, and it's certainly much smaller than the atoms. All right, and there's a 500 or 600 or 700 atoms worth of polarization here. So you're out of luck in having something called a photon interact with one electron. What really happens is one bit's interacting with this electron, there's another bit interacting with another electron, there's another bit interacting with another electron, and they'll be leaving at certain times based on the energy that's coming in, and there'll be a certain frequency, and they'll just scatter those little bits, and there'll be places on surfaces where you'd reconstruct the right frequency, and that's all that matters for calling it a photon, is that it has to have the right pattern of applying its energy. And that gets us back to the simple pendulum argument that the electron is in tension in an atom. There's the proton here, and the electrons are in tension with each other. They don't like each other. And the trick is you want to move this electron from here to over here where this other atom is, and you're going to push that electron out, essentially, okay, and cause a chain reaction. Technical difficulty of some kind. Anyway, picking up where I was. Frame rate's not quite right either. I'm going to fix that. Anyway, so the polarization is very large, has to happen to hit 2 electrons each, and it's really just about the fact that the electron is going to move because of the first piece of momentum that hits it. And what you really need to do is to make this possible so that another bit of energy, whether it's this electron or the electron next to it, or this, doesn't matter which electron, that this another pile of energy hits and takes advantage of that movement and causes even more movement. And that would be the photoelectric effect, is the fact that you constructively added the energy, and it really is a timing thing. So the same timing that's creating a photon, that is the movement of electricity through a conductor, let's say, you move electricity through atoms, and one atom fires, and then another atom fires, and another atom fires, in the sense that the electron moves in a direction, pushes force, and that's really all you want to do is push it. You push some stuff. I push some light, and then somebody else pushes some light, and then somebody else pushes some light, and when you add up those three pushes, they have a timing cycle from those three individuals on a location, and the timing will be is that they'll hit at the right frequency, and that right frequency means that they will push on a piece of material. They'll hit it, apply energy at the speed of light. The energy is going to move like electricity through the atoms, and then they're going to apply another piece of energy that's going to push it even faster, and that's the key to kicking the electron, ionizing the atom. So you don't ionize the atom, first you electrify it, and then you ionize it when you hit it with another piece of energy, and the piece of energy has to be behind, of course, the first impulse. So the impulse is moving through here, and it needs to get hit right when it's at the right location. So that's why it's frequency dependent, and that's why polarization matters, is because the energy has to come at the right time to hit behind the thing you're pushing. It's moving this way. It's a moving target, like a duck, so for hunters or something. And you got to hit the duck twice. So you hit the duck here, and the duck's still flying, not very well, but he's flying, and then you need to hit right there behind the duck to knock him down. Okay, and that's the trick to it. That's why frequency is important. Yeah. So that should be enough of a background, I think, to explain well enough. Give you some context.
Prediction by containing some number of quanta. But at high enough frequencies, the energy quantum will be more than kT. These modes either have to have no energy or more energy than, on average, is thermally available. So at higher frequencies, the probability becomes greater that a mode will have no energy at all.
That diagram was really poor, right? I'm sorry I didn't freeze it quickly enough. But I mean, it had low frequency with lots of bars, and then high frequency with only 2 bars. I mean, it's completely backwards, but whatever.
This is how the quantum hypothesis explains the drop-off of radiation intensity with increasing frequency.
Obviously, increasing frequency is more momentum, right? It's more little bits. So obviously, the profile has to drop off. That is, the number of photons you're going to be able to produce drops off because you're using up all your bullets, right? So if I shoot bullets in 3 seconds, once a second, and then somebody else is shooting bullets, 10 a second. Obviously, the guy with 10 a second can't shoot as many series of bullets because he's using up 10 every second, right? So his ammo runs out.
Planck's skepticism about the quantum hypothesis was understandable. Radiation takes the form of electromagnetic...
Well, I wish it was understandable. I wish any of this was understandable in terms of recognizing that the theory was really bad. It's really a mess. And instead of just conceding you don't understand it well enough, you just wanted to write it all in cement. And so you just like cement heads, and then you started just cheating. I mean, the math for the double slit was wrong the day Young drew those 2 waves coming out of the 2-slit experiment. It was already wrong. It was wrong that day, and it's been wrong for 200 years. And you've been lying, essentially. Your physics has been lying for 200 years, pretending that analysis is correct. When it was wrong then, it's wrong now, and was wrong in between.
Like waves, and the energy of a wave is distributed throughout space. How could this energy exist in discrete chunks? Discreteness is something we associate...
Well, I don't understand how you could ever think a photon was anything other than a discrete object, in the sense that it's pixelated. We've certainly known that for a long, long time, that it lands in tiny little locations. I mean, come on. That isn't hard to observe.
Associate with particles, not waves. and nobody had ever seen direct evidence of any type of radiation particle.
Nobody had seen direct evidence of a wave either, so that doesn't mean anything. I mean, obviously we don't have direct evidence of photons. We can only understand them by them being terminated somewhere. They can only interact with matter. They don't have any other function. If they're not interacting with matter, you can't know they exist. They only exist, in a sense, in any meaningful way when they hit something. Other than that, they're inert to the function of the universe.
But then it was pointed out that such evidence had indeed been observed in a phenomenon called the photoelectric effect. A solid material contains electrons, and these can be pulled loose by supplying electrical energy, as is done in a spark plug. Energy supplied in the form of light should also be able to remove electrons. But if a material is illuminated...
Again, also should by what? Your theory? I mean, there was no reason to assume that photons necessarily were capable of generating enough energy to produce something like a spark. So we know a single photon certainly couldn't have done it. You know, if you could imagine, though, that you can take a magnifying glass and concentrate a bunch of photons and create something that can burn holes through other things. So, you know, we already knew light contains energy, so why are we pretending we didn't know that?
with low-frequency light, represented in red here, no electrons are ejected, even if the light is very intense.
Yes, even though you're sending a whole bunch of it, because you're not hitting it at the right timing cycle. It's a pendulum. You have to apply the energy constructively. So it's really funny that they so emphasize this constructive and destructive interference pattern kind of jargon, and yet they really don't understand what resonance is. They don't understand that all it is the atoms are a system, and if you want to move the atom in a direction, you can't apply the energy in front of it. You can't if I want to push something by throwing firecrackers at it, I have to keep throwing the firecrackers behind it. If I start throwing firecrackers ahead of it, then I'm going to have it going in the wrong direction. I'm going to lose momentum in that system. If I want to maximize how much speed I give the person, I have to keep hitting. I have to keep pushing them from behind. If I push them from in front, if I throw my firecracker way too soon or way too ahead of them, that'll be completely destructive to my purpose. And that's all that this is about. Is a photon is a pattern. The pattern has to be applied to the electrons and the atoms based on what those atoms are going to be sensitive to. They're going to move a certain speed, so you have to be adjusting how you apply the energy to adjust to the speed of the atom you're electrifying.
On the other hand, if the illumination is high-frequency light, represented here in blue, electrons are emitted, even if the light is very weak.
Even if there's less of it, yes. Each photon, each package of momentums, each ray, okay, each row of pieces of momentum is hitting in the right sequence, where it's always hitting right behind the electron, and therefore it pushes the electron fast and faster than fastest. And how many you need, I'm not certain. 2, 3, 4, but it's some small number. It might just be 2. Photons might just be 2 clumps of energy this far apart at a frequency this far apart. You know, they're in space this far apart, and they're in space this far apart in those 2 dimensions. And they're just 2 particles, one here and one over here, one here, one here, a diagonal line between them. And that's what's flying through space, and that's what causes electrons, atoms, to become ionized. But the same electron you hit with the first bit won't be the same electron you hit with the second bit.
It was Einstein who in 1905 explained this by considering Planck's quanta as particles moving at the speed of light, what we now call photons.
Right, so this is where the vocabulary sort of got broken. Did Einstein mean photon was a series of bits of momentum, or did Einstein think photon was a clump of photon, one big particle that said I have a frequency? You know, a round ball that just says 500 nanometers on it, even though that doesn't make much sense.
It
doesn't make any sense, really. It clearly has to be a pattern, a frequency of interaction. The whole thing has to take place over a period of time. Photons are produced over a period of time, and they're received over a period of time. And they just broke all of that by trying to say photons just, instantaneously pop out of a substance, and they instantaneously are received by a substance.
The energy needed to remove an electron. Only a photon with an energy greater than W can eject an electron. The total light energy, which represents the number of photons striking the material, will determine the number of electrons ejected, but not whether electrons are ejected.
Right. So again, it's just back to the simple argument. If you have the wrong frequency, you'll end up throwing your firecracker in the wrong place and pushing things in the wrong direction. But if you have them lined up right, the first one goes off, pushes. The second one goes off, pushes more. And that's the idea. Constructively adding the momentum or destructively adding the momentum. That's all there really is.
And the kinetic energy of the ejected electrons will simply be the energy left over from this photon-electron process. On the other,
the greater velocity, the velocity to leave and the velocity to leave quickly. That's all the difference will be. You'll make it go fast enough to get over the hurdle, let's say. Say you have to, the electron has to jump a stream or it has to jump something. Having enough energy to jump it is the standard, and then having extra, jumping twice as far as the stream, it's a nice bonus. Okay, so if you can get it going really fast, then you can jump the stream by a large margin, and that's, but that's the difference, is you can't, the energy is conserved.
On the other hand, a photon of low frequency light does not have enough energy to free an electron. So even if there are many such photons, that is, the light is very bright, no electrons would be ejected from the material.
So this isn't absolutely true anymore. They kind of do know that if they have really intense infrared light, the fact is that some electrons will be ionized and pop out of the surface. And I would argue the reasoning for that is that you coincidentally create circumstances where you're actually, because you're hitting the surface with so many little bits, some of the bits of the big frequency are completely 180 degrees out of phase, and they end up converting the photon into a ultraviolet photon. If you took infrared frequency 500 nanometers and you put another one out of phase right on top of that photon, you'd end up essentially with a blue photon. But you can only do that if you're hitting the surface with an awful lot of little bits of energy.
Thus, Einstein explained how Planck's quanta manifest themselves as, quote, real particles of light.
So again, the photon is a pattern of real particles. That would be the thing to say. That would be the way to fix this statement. Photons are a pattern, and it's a pattern of particles. Now you have a good answer. You have an answer that answers all of the questions.
A more prosaic example is how photons explain sunburn and sunscreen. If you look at the spectrum of solar radiation, you find that the great majority of the energy is in the visible and infrared regions. Only a tiny fraction is in the high-frequency, short-wavelength ultraviolet region.
So you can sort of understand that it's a little harder to create machines that can jiggle electrons very, very fast. So it's just the odds of. You can make a machine that does this really easy, but it gets harder and harder to move stuff quicker and quicker and quicker, and so they're just less probable. It's less probable that you'll be able to get an electron to move at these quick speeds inside of the atoms. It's just less probable. And it's a lot easier to get them moving around at these slower speeds within inside the atom.
Yet sunscreen protects us from sunburn by blocking only this small amount of UV radiation. Let's assume the chemical reaction responsible for sunburn requires a certain energy W, and light is composed of discrete photons.
So again, we're just back to this bullet firing and resonance. This is only about the fact that each one of these substances is going to have a different sensitivity. The energy of the electron, the electricity, will move at a different speed depending on the atoms. So it's a subtle difference, but it's an important difference in terms of adding momentum to the system. And so each one has a sensitivity in the sense that there's a speed that the little ball will roll, and when you're adding your momentum, the frequency is deciding whether you're going to hit behind it or ahead of it. Whether you're going to add energy or you're going to not add energy. And that's all that's being decided. The frequency is just telling you the speed at which electrons can move in different chemicals. And so different chemicals will react to different frequencies.
If a molecule absorbs a photon of energy less than W, there will be no chemical reaction and no sunburn. If a molecule absorbs a photon of energy greater than W, then there will be a chemical reaction, leading to sunburn. For sunburn,
and again, the absorption argument, that they all absorb. There's no such thing as not absorbing the photon. So the photon always is, the energy of the little bits of the photon always go into the surface and always move in electrons, and are always doing that. And the point is whether the energy is released back to the environment or whether it stays inside of the object. But the fact is they all interact, and they all, you could say, make it hot to some extent, or at least heating the surface. So they're all interacting, and it's whether or not you send the heat eventually is going back, and the question will be is what form will it go back in? Will you send it back as a high frequency gamma ray, or will you send it back as a low frequency infrared? And obviously if you send back the energy in packets where the energy is slow, in the sense that, less bullets, then you're going to have more of those photons to get back the same amount of energy than what went in. So, obviously the gamma ray has 1, 2, 3, 4, or the ultraviolet light has twice as many bullets. So, obviously the single photon of both of those things, you have more bullets to send back or to absorb with the higher wavelength, the higher frequency energy.
Acquired energy corresponds to photons with frequencies in the ultraviolet region of the spectrum. So by blocking only a tiny fraction of the sunlight's energy, our skin is protected against sunburn. The great majority of the sunlight's energy still reaches our skin, but no single photon corresponding to these frequencies and wavelengths has enough energy to cause sunburn-inducing chemical...
Right, well, it's not no, so we're still getting hit by X-rays and lots of other kinds of crap. But there's, just not enough of them to do a substantial amount of damage. And the damage is just ionization. All you're really saying is the difference between just moving electrons around and ejecting electrons, that is, ionizing the atoms.
Changes. We've seen that there is strong evidence that light consists of discrete particles we call photons, having energies given by Planck's formula.
So if you see, he said it right there. He says that the photons are made essentially of discrete particles. Now if they said it that way, then they'd understand it's like these little dots here that he's drawing as atoms. No, the little dots are what the photon is made out of, and it's interacting with bigger dots that are electrons. And it's not interacting with a single electron ever. Obviously a piece of the photon is interacting with a single electron, but you need atoms to make photons, and you need atoms to receive photons as coherent things, because what you're really doing is using electricity to produce them and electricity to receive them. You're receiving an electric current. That's how we detect photons. Technically, it's the same kind of thing that's producing them. When some piece of chemistry is burning, you could argue that the fire is the electricity of the atoms splitting apart, pulling away from each other. It's a bunch of electricity. That's what fire is.
But it had long been firmly established that light is a wave phenomenon. If you put a small pinhole in an opaque screen, place another screen to its right, and shine a beam of light from the left, then on the right screen, light intensity will display a...
Alright, so this was wrong 300 years ago, right? So Newton already dispelled this notion. This isn't what happens. So again, where did these people, these are smart people talking about physics, and yet they keep doing this, and don't they know that now that's just nonsense? I mean, Newton's rings, we already know that doesn't happen. It's more than just spreading. We know that some of the light goes straight through because it's very bright here in the center. That's what this peak means here, right? That's why he's got a mountain here. It's right in the middle. There's a whole bunch of light. And then it gets very, very dim as it goes sideways. So, and we know now that the real truth is that this is an interference pattern, that there's light from one surface going a vector, and there's a vector from the other surface going to a location, and that's making the photons. When they're in phase, you've reconstructed photons. Where they're out of phase, you haven't. And so this hill gets broken into little shreds, but this middle part doesn't get broken. So the truth is 90% of the light goes straight through, spreads a tiny bit, like all light spreads, even laser beams. But the rest of all the fringe light is all being created by scatter, by light that's being deflected, and it's being deflected by the surfaces. Their math knows that. Like I said, and this drawing was wrong 200 years ago, and it was wrong 300 years ago, and yet they're still drawing it today. And so you say, what kind of credibility does physics have when they can't draw a single opening, and they can't do that correctly? I mean, in any way honest to what is known fact. I mean, well established fact. I mean, overwhelmingly established fact, and they're still drawing it like this. I mean, and then you're going to trust them when they talk about other experiments they've done, when they can't draw the simplest experiment you could have, pretty much, and they can't draw it correctly? Come on. You really can't trust them.
So-called diffraction pattern that is the unmistakable signature of a wave.
Yeah, so again, more of this unmistakable wave nonsense, when no, all its scatter does exactly the same thing. Scatter does exactly the same thing. I don't know why I would think that the only thing in the universe that can possibly spread is a wave. I mean, why would I think that? Lots of stuff can get spread out, Doesn't have anything to do with, a wave. I mean, there's just so many examples.
If you open a second pinhole so that another diffraction pattern appears on the screen, a very rapid variation of intensity called interference fringes will appear.
Right, so we know that this doesn't work. Okay, this diagram, their two-wave concept doesn't produce the right pattern. So it's wrong. It was wrong 200 years ago. It's still wrong. It's always been wrong. There's actually there's four waves if you want to draw it correctly, and the four waves are in idiotic locations. They're right. The wave center is on the surface, meaning that somehow the wave broke for no reason right dead center of the slit, and somehow it went through the impediment. Somehow the wave is doing stuff that just doesn't make any sense. But you have to have four waves. Two waves, wrong math. It doesn't work. Broken. Catastrophically wrong. I mean, not just a little bit wrong, but completely wrong in anything but two extreme examples, where I make this impediment infinitesimally small, or I make these openings infinitesimally small. That's the only way they can make it work, because they'll take away two of the measurements, right? If I make the distances really, really tiny between the surfaces, then your math becomes irrelevant, because 32 and 32.7, those two numbers are so close to each other that you just call it 32, right? So I have lost the distinction between the surfaces' distance. I've taken away their power to make a different pattern. But that's it. That's the only way they can make their math work, is to have two very unlikely demonstrations of the experiment. The 99% case, where you have a reasonable opening and a reasonably sized impediment, their math fails dramatically to identify the proper locations for where the brights and darks will be. And they just keep doing this, and no one stops them, and no one says, hey, wait a minute, we got to quit doing this bullshit physics. And I've been saying this for years now, and just nothing. Absolutely no concession from anyone saying, hey, that's really bad physics. Nothing. And it's, very depressing that smart people are so dishonest.
These observations are a slam dunk for the wave theory of light.
He just said it. If Lewin has said it, they all say this kind of crap, and it was never right. It was superficially, similar. It looks a little like, but that's all it ever was. And it's just calling a gorilla Sasquatch. Calling a bear Sasquatch. It's a horrible cheat of reality.
Let's look at this experimentally. First, we take an image immediately after the pinhole screen. This shows light emerging from the two pinholes, one large and one small.
Yeah, I don't know why you would do the small and large thing, because that's just going to make it's harder to see, frankly.
Next,
it's like using non-monochromatic light. It just messes the pattern up rather than making it more visible. So obviously, this is Newton's rings. Why didn't he draw it that way? Why he drew big hump here, big hump here? That's what he drew, pretending that they only do this pattern thing when there's two of them. No, a single hole this size makes small rings. A single hole, large. This is the large one. The large one makes the small rings. The smaller the hole, the bigger the rings. The bigger the gap in the rings.
We take an image some distance away from the pinholes. Here we see that the light from the pinholes is spread out into ring diffraction patterns. Notice how the rings for the large hole are more closely spaced than are the small hole rings. These features are precisely explained by the wave theory of light.
And they're precisely defined or described by the pattern theory of light also, the pattern of particles. The pattern of particle theory has no problem with this either. The light scatters at the surfaces, and all you're doing is saying you're remaking a photon where you put the frequency back together. And when the frequency is not back together, you don't see a photon. And when it's back together, you see a photon. So it takes the little bits of the photon, scatters them to new locations, and 50% of the time they will be in phase, and 50% of the time they'll be going out of phase, right? They'll either be getting into being completely in phase, or they'll be in the process of going completely out of phase. So you can understand it'll always be 50-50. It turns out that the light bands are bigger than the dark bands because the photon can be a little bit out of phase and still be seen as a photon. It doesn't have to be perfectly 500 nanometers between each dot. It can be 480 or 512. You can be a little bit off and still have a photon.
Moving even farther away from the pinholes, the ring patterns grow in size and overlap more. And looking at this in more detail, we see closely spaced vertical lines superimposed on the diffraction patterns. These are interference fringes, and there's no reasonable way to explain these observations without invoking the concept of waves.
So there is a reasonable way. He's just making a declaration like he tried to figure it out, and he didn't do any of that. This idea of saying there's no other possible theory. What, did you try to think of all the possible theories? There's no other possible explanation. Those are bold, that's awful bold talk. And it really is irrelevant to sort of the argument. You have to make the argument that, well, this fits so well that, there's no reason to doubt it. It so completely answers the question. But you already know that your quantum mechanics doesn't completely answer the question. So, so they can't make the argument from the sensible position of explaining why their evidence is so good. They're trying to say the other guy's evidence is really bad. And that's really not the way to do the trial. The trial is to present your good evidence honestly, and not pretend, that you know the other evidence when you never even looked at it.
Now, we think of a particle as a little thing at a single point in space, possibly moving in some direction at some velocity. And we think of a wave as something spread out in space, oscillating with some frequency.
No, that's not even how I think about it, frankly. I think about a wave as being a wave of something. Stuff is waving. Matter, some sort of stuff, and to have a wave, generally speaking, you're arguing the stuff has to be connected. There won't be waves of sand, so to speak, right? Okay, it's really hard to make a bunch of sand wave, without waving the container you put it in or something, without waving some other medium. So, I mean, these have to be connected little bits of stuff that you're waving, where you're causing all kinds of momentum in different directions that the atoms are taking care of doing the math. And the particle is an independent little thing. It's not tied to anything else. Now, I can take soldiers and I can say waves of soldiers. The soldiers aren't tied to each other. There's no ropes tying them to each other. There's no connection necessarily. They can all go in individual ways, but I can make them look like waves. Bullets. I can fire bullets from a gun and I can make them look like a wave of bullets. But the wave of bullets, none of the bullets are connected to each other. Any one of the bullets can go off in any direction and it's not going to affect any of the other bullets. That's the... he doesn't make a nice conceptual distinction between this wave and particle. And that the fact is, it's easy to make particles look like waves. It's really hard to make waves look like a particle. And that's should be a giveaway, that the answer is yes, the particles can look like a wave. This isn't waves looking like particles.
If light is so precisely described as a wave, but also displays unmistakable particle properties, then what is it exactly?
It's particles that sometimes look like waves because they're in a pattern. And the pattern can look wavy, but it's not waving. There's no medium waving it. It's just that you have produced it in a form where it's mimicking the function of a wave, but it isn't a wave.
A photon. How do we picture it? The answer is not very well. We could draw a little wiggle indicating a wave-like oscillation with an arrow indicating
Yeah, it's very bad. What you should be drawing is a dotted line, and then you should be drawing a dotted line that's out of, that has polarization. So you should be drawing a little dot, and then a little dot, and a little dot, and a little dot, and then an arrow, indicating that it's little dots at a frequency, and the frequency has a polarization. And then you'd have an accurate description and drawing of a photon instead of this inaccurate impression that you give.
Particle-like thing moving in some direction. But the fact is, we simply don't have any day-to-day experience with something that has the properties of both a wave and a particle.
So we do. So he just said we don't have any day-to-day experience. We have all kinds of experience. Like I said, wave of bullets. I didn't invent that phrase. Okay, it's been around. Are the bullets really waving? No, they just look like it.
So we don't have a frame of reference in which to understand such a thing in any intuitive sense.
So again, he says it, and we don't have any references that I can compare this to. Wave of bullets. Yeah, you do. So I mean, it's like they didn't even try to get the right answer here, and this is just part of all this propaganda. So his teacher told him that crap, and then he recites that crap. And it's just crap because, yeah, we have lots. I barely even trying. If I really try to go find all the places where you see a wave and it's really just particles, I mean, there's probably lots of examples. If I can give you a wave of soldiers, wave of bullets. There, I've got two really good ones right there. And there's probably many, 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 many more.
We've seen images that clearly show the wave nature of light.
So again, it just clearly shows that there's that photon is a pattern that you can break and make. Break and make, break and make.
We've also presented evidence that argues for the particle nature of light, but we haven't actually seen light particles with our own eyes. So, reasonably, we might...
So that is kind of funny, right? Because you haven't seen light waves with your own eyes either. This never is about seeing it with your own eyes. This is about the fact that it's one of the smallest things in the universe. Probably is the smallest stuff you can get. It's like seeing the gravity particle. Because it's all the same, frankly. The same stuff. All the stuff moving the speed of light is made out of the constituents of these little bits of momentum. And all you're doing is putting them in different form, different shapes. And by shooting them in different configurations, you create different manifestations of energy.
I'd still be skeptical about that, especially since the implications are a bit mind-bending. Fair enough. What if we repeat the pinhole experiment, but with light so weak that at any given time there should be no more than a single photon in the system? What will we see?
Right, so this is the dangerous experiments where they've never done them, and they can't be sure of what they're saying. You know, they can't make this single photon thing. As he just pointed out, we're not very good at controlling perception of a photon. And so this is, you know, just it sounds good, it's blah blah blah. You know, I fell for it 10 years ago. Yeah, they can do that. But no, they can't. They don't have a machine that makes single photons.
Doing this successfully requires extremely sensitive equipment, but it is possible. Here we're going to look at frames from
So he says again, it's possible. So we're just going
beautiful video titled "From Photons to Waves" that shows the result of this experiment. The link is given below.
Yeah, well, that isn't very helpful. I have to type in all that crap? I mean, thanks.
After a short time, we see a seemingly random pattern of dots. These are the images of individual photons. A while later, more photons have arrived, and there's a hint of some sort of pattern emerging.
All right, so let's understand how they do this experiment. So it's sort of, you can understand how, oh, there's a mistaken assumption here. You know, and that's, you know, it's always the case, right? It's always a case of some kind of assumption that was just a little too premature. So the idea is you have a light source. Okay. And then you put something to block it, to block out the photons. And so fewer and fewer photons go in. So you just make more of these, or you just make them thicker until very few photons are over here in your receiver. But the technical problem is that what could really be happening is all you're doing is making little tiny pores in the surface, right? I mean, if a photon gets through, it goes through a tiny hole of some kind, a little hole. And so what you're doing is just creating little scatter bits off of that little hole there, and little scatter bits off of this little hole here, and little scatter bits off of this little hole here, and little scatter bits off of this little hole here. And there's so few, you know, these bits flying, that the odds of the photons, okay, over this distance, landing here at the right sequence, okay, getting their frequency back, so the right phase, putting them back together, it's just a long odds, okay, that happens. But the fact is that you just don't know how many times that could happen or when that's happening. You're just saying there's only this number of photons. So it's not that there's not photons flying through this environment constantly. Of course there is. And then the trick is we put a slit in here, right? There's only a certain number you're collecting at the surface. Well, the irony is if I put a slit in here, I'm actually going to help put the photons back together, because now I'm going to have a shorter distance between where the interaction between the little bits will be and where the surface is that I want to remake a photon on. So, but clearly I could have a little bit hit this surface and a little bit hit this surface, and then the right frequency and the lines line up, and I can have the math work. So in a sense, putting the slit in makes it possible to remake more photons, because I'm taking away the scatter distance and I'm creating two sources, okay, that we know can create a photon when they're hit by light from, you know, this original source is pumping it out, bang, 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 bang. And we want light from the same bang point, the same electricity point. And so the other point to point out is that's what's happening when you're making light. To make a single photon at a time, you'd have to have just one electron on the whole wire, just one electron move, doot, 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 you know. And that's not the odds, right? The odds are is that you're sending a whole bunch of atoms are getting are getting manipulated by your voltage, a whole bunch of them. So you're creating a whole bunch of chains of electricity running through the wire. And each one of those chains is going to be producing photons. So you're producing lots of photons with each pulse of electricity. So you just can't. The point is there's no reason to assume single photons are actually in the environment. You're just talking about the probability of reconstruction. So the more I spread all of the photons, the smaller I make the slit, you can sort of understand a hole, the more likely it is to be all fringe pattern and no straight through pattern anymore. If I make a slit smaller than the wavelength, the polarization of a photon, you can understand that every single photon will get broken. No photon will get through. So if I make the slit smaller than 500 nanometers, I'm guaranteeing, essentially, that every single photon that goes through is going to be broken. There's no way for part of the photon not to hit the surface. So only part of the photon can possibly get through the slit. Only pieces of it. So I'm automatically creating a bunch of pieces.
As time goes on, the pattern becomes clearer, while the contributions of individual photons are no longer so apparent.
So again, every time this is done, it's always done with the same kind of experimental equipment where we don't even see the sidebar pattern. So we're not getting a very good view of the pattern. So that's always part of this too, is why don't they have better equipment, where they can scan the actual fringe pattern. And it's never done, well, like I said, there's lots of ways you can try to minimize, but the point is always going to be is that there's no way for you to guarantee you don't have the pieces in the environment. And the only math that works, again, you have to recognize, the only math that works, there has to be photons at both surfaces. There has to be pieces of photons being created at both surfaces, or there just can't be any reconstruction.
We finally have the fringe pattern that characterizes wave interference. Yet we've seen that it's actually built up from a great many point events. The light energy...
The point events are just the reconstruction events, so they're happening whether you're throwing very few photons or a lot of photons. It's always remaking photons one photon at a time, so that doesn't mean much.
It does indeed arrive at the image in discrete photon packets at specific places at specific times. Yet somehow the photons, quote, know how to arrange their arrivals so that after some time the average effect of a great many photons is to create a wave interference pattern.
Right, well, so we just threw in some Feynman nonsense there that somehow there's this random idea and all of that crap, and no, you don't need any of that. All you need is, like I said, you scatter them off the surfaces, the pieces have a 50-50 chance of rearranging back in phase. And so that explains the pattern.
So we have a wave picture in which interference patterns are the result of a wave passing through two pinholes.
Right, and that doesn't work mathematically. It doesn't make any sense at all. It can't work, can't make the more complex real pattern of the double slit pattern, which has the two patterns overlapping each other.
Or slits, creating two diffraction patterns that spread out and overlap. But we also have a very convincing particle picture, where light energy is concentrated in photons, which occupy a particular place in space at a particular time. We typically think of a particle as being at one point at time t1 and at another point at time t2.
Right, so we typically think that photons go right through the slit, and that's the whole problem right there, is that the photon doesn't go through the slit. The one piece of the photons, each pieces. And obviously because of the polarization of the light and depending on how close the slits are, the surfaces are breaking a lot of photons. A lot of photons are breaking at the surfaces. Their bits are being scattered, and that scatter can rearrange back into a photon. You can reconstruct a photon. So the pattern is really photon reconstruction and photon destruction in the sense that you didn't reconstruct, non-reconstruction. The frequency is off, therefore you can't receive it as a photon. The frequency has to be consistent, just like a radio frequency has to be consistent, or you're not going to receive it.
And therefore having followed some specific path between the points. But we've seen that photons arrive at the image screen in accordance with an interference pattern. Do single photons interfere with themselves in the presence of two slits? If so, then how does a single...
So we know that force doesn't interact with force, and we know all these things. We know we can't shoot lasers into lasers. There's no reason to think the force bits could ever interact with each other, so why are we even thinking that's a possibility? It's not a good answer.
Particle pass through two slits at the same time. Or, if the photon only goes through one slit, then how does the existence of the other slit influence how the photon arrives at the image screen?
And it doesn't influence how it arrives. It just the only thing you're doing is taking a pattern in, and you're saying, where did I remake the pattern out? And that's it. Pattern in, pattern out. And you'll have less pattern, less photons will be hitting the surface than in front of the surface, because some of the photons will be, in fact, remain broken. So what you can clearly know is if I detect how much light is in front of the slits hitting the entire surface, it'll be far less light that's hitting the other surface. Well, not far less, because as stated, a lot of light goes straight through the slits. And that light's obviously not going to be degraded at all. But a high percentage of the light, depending on how small the slits are, if I do small slits, a high percentage of the light will in fact be broken, and I'll get much less light on the target than if I measured the total light that was being admitted to the same surface area in front of the slits, and then measure how much light got to the target. There'll be much less light at the target.
This is one of those nobody understands it moments. But the problem is in our own heads. There's a precise mathematical description of this whole process. Light energy manifests itself as...
That's just nonsense. So obviously it's not precise and any of that stuff. So it gets the wrong answers, completely wrong answers. So that's just nonsense.
3 photons, each with a certain energy and arriving at a certain place at a certain time. This occurs at random, and the classical wave intensity is just the probability that you will find a photon at some place and time. What paths do the photons follow? That's not part of the theory. And in fact, it doesn't even appear to be a meaningful question.
So now they've really, just made everything crazy physics in the sense that, we're not supposed to care about how it actually happens. That's just for silly people. We have a probabilistic, mathematics that tells us how dice can possibly arrive at a location, and we really don't need to think about how to roll them. Just like flipping a coin, right? I mean, if I put enough randomness in, that is, I flip it with enough noise, I won't be able to predict the results, and I'll get a nice 50-50 distribution as a probability. But the fact is I can turn down that noise, and I could go just a little bit of energy. And now the math doesn't work at all. The math completely fails, because I can make it guaranteed that it's going to be, heads 90% of the time. By just flipping it less. And likewise with dice, you can manipulate outcomes, and that's a fact. By understanding the fact that you can change the variables, and by that changing the variables, you can change the outcome. This has nothing to do with any randomness built in. It just has to do with the fact that yes, the scatter, is going to be random, and the outcome is 50-50, and that's the general. Again, it isn't actually 50-50. So again, I'm cutting a corner just like they cut corners by saying it is. It isn't. More photons, they're more likely to be reconstructed than destructed. They're more likely to be. You're more likely to be within the phase close enough to the right phase. So you'll get more photons being reconstructed than photons you couldn't reconstruct.
asking into simply trying to force our limited concepts of particles and waves onto a realm of nature where they don't seem to be as valid as they are in our macroscopic world.
Yeah, so this whole idea of just breaking logic and physics, and we don't have to think about momentum traveling through 3 dimensions of space, and instead we can turn physics into some mushy religion.
Cool. Let's continue to try and push back against the idea of particles of light. We might argue that real particles carry momentum, and you can exert force by scattering them.
So why did that even happen? Why did all of a sudden this nice distribution of energy in direct directions all of a sudden turn into energy going in all wrong directions? So again, that's all part of this physics too. If you understand real kinetics, the fact is that you can have a system where things hit each other and they just replace each other. The thing going this way hits the thing going this way, and this thing goes that way, and this thing goes that way, and they just exchange their positions. They exchange their identities. But the universe doesn't change at all. There's still something going that way, and there's still something going that way, and it's like they didn't interact at all. That's real kinetics.
Off of other particles. If light is composed of real particles, then you should be able to push an object around by shining light on it. Well, it turns out you can't.
Yeah, so that's, I don't know why you'd even doubt that one. But this is all part of saying that the photon doesn't have any mass, and it doesn't have this, and it doesn't have, and it's just all crap. Forces aren't the same thing as matter. There's no point in measuring its mass because it's not the same thing as matter.
In classical theory, light has 2 components, an electric field and a magnetic field, shown here as red and blue arrows. The length of an arrow signifies the strength of the field at that point. The fields are perpendicular to each other and to the direction in which light is moving. Now suppose the light passes by a charged particle. Classical theory predicts the phenomenon of radiation pressure.
So obviously none of that stuff has any relevance at all. It's all nonsense. It always was nonsense. There's absolutely no evidence that a photon has any electric components, no evidence that it has any magnetic component. You can't bend it with magnetism, blah, 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 blah. Just nonsense.
This slide is...
Electrons have those properties, and photons interact with electrons. So they're really just measuring what photons do to electrons. They're not really measuring what a photon is.
A little technical, but in the end, the important thing is the final result. The steps are just for completeness, and there's no need to follow them. Radiation pressure works like this. Suppose at a particular time the charge Q sees an electric field E and a magnetic field B, which are moving in the direction S.
So there's no even point, right? There's no fields. Fields are made out of real things. The real quanta hit stuff. So this is just more babble, just nonsense. There's an electric charge Q is usually in a matrix of matter, and that means the charge Q has a disposition where it's stuck in the matter. It's between electrons and protons. It's in tension. Then you hit the tension that it's in. So again, they're trying to make the tension in the photon. The photon doesn't have any tension. Okay, the electron has the tension. So again, they're describing the electron. They're really not describing the photon.
The magnetic field strength is the electric field strength divided by the speed of light. Suppose the charge is moving with a velocity v. The electric field pulls on the charge with force Q times E. The energy of the field transfers to the charge, which we call the work it does.
Yeah, so none of this makes any sense because you know that this Q, this electron, okay, the photon, in fact, as a pattern, is much bigger than the electron. The bits are smaller than the electron, but the pattern is bigger than the electron. So obviously the whole pattern that is a photon can't possibly interact with this one electron. So all this is just mush.
Is this force times the distance the charge moves? The distance is velocity times elapsed time, so the field does work EQ VT. The magnetic field will also exert a force on the charge. A force exerted for a given time transfers a momentum of force times time. The force exerted by a magnetic field on a moving charge is the magnetic field B times the charge Q times the velocity V.
I wish I could just skip through all this because, again, this is just telling you this is just their formalization of the fact that there's momentum there's a condition that exists. You take the condition and times the momentum, and you can figure out what the new outcome will be. But it's just basically saying this is the math for hitting an electron with momentum, and the electron is already in a previous condition, and if you know what this previous condition is, you can deduce which way the momentum will be added.
For an elapsed time t, this transfers momentum B, Q, V, T to the charge. The magnetic force is peculiar in that it pushes in a direction perpendicular to both the magnetic field and the charge's velocity. This is in the direction S. We see that the momentum expression...
They are just conveniently converting, so they're using one field to create momentum in an arbitrary direction, and then they fix it by creating the momentum in the opposite direction, and the outcome again will be just the obvious one, where the photons, whatever the direction is of the photon, the vector that the electron is going to take is going to be somewhere forward, okay, to that momentum. That momentum will not be in the opposite direction, so there's no pulling photon. Photons only push; they do not pull ever, in spite of their nonsense about virtual photons. There's no pull.
Is the same as the work expression, except the E field is replaced by the B field. But the B field equals the E field over the speed of light. So we have the following result. If light transfers some energy to a charged particle, it also transfers a momentum equal to the energy over the speed of light. And the transferred momentum is in the direction that the light is traveling. The reality of radiation pressure was spectacularly demonstrated by a recent Japanese space mission to Venus, which deployed a so-called solar sail to use radiation pressure from the sun to accelerate and navigate the spacecraft.
I mean, I just don't know who would ever even have any other feeling about light besides the fact that, yes, of course it's pushing things. Of course it is. It's just not very effective.
One more detail before we summarize all this. If a light wave propagates at the speed of light, c, for 1 second, it travels a distance c. We call the distance between wave peaks the wavelength lambda.
I don't know why you'd say the distance is c. That's really bizarre, but anyway, it doesn't matter.
Light frequency is nu, then in 1 second there are new wave cycles. So new wavelengths must add up to the distance c. Therefore, the wavelength is the speed of light divided by the frequency. That is c over nu.
I don't know where frequency and nu are the same thing. I don't know why they're drawn as v. I mean, that's just too weird.
So the takeaway from this discussion is that if light consists of photons of energy E equals h nu, then the existence of radiation pressure requires that those photons must have momentum P equals E over c, which is h nu over c, which is h over the wavelength lambda.
So again, you're stuck with this idea. Again, you're still stuck with the idea that, look, it's just stuff at a frequency, and you're saying the stuff is equal, and you're just saying how many pieces of stuff can you fit in a certain amount of space. The more stuff in the space, the more mass it has. And so this is just a mass equation in a sense. You're just saying how dense is the photon. The higher the frequency, the higher the density of photon. Nothing more complicated than that. But the real trick is that the density is really being decided by the polarization, because your polarization is getting smaller and smaller as your wavelength gets smaller and smaller. And it's the polar. You could just write this equation, and instead of using the frequency, you could use the polarization of the light, and it would work just as well.
So photons do indeed carry momentum, just like we'd expect for, quote, real particles. Later, we'll see that this relationship between momentum and wavelength will provide a critical insight when we try to understand the behavior of electrons. The proverbial final nail in the coffin of skepticism towards the photon concept.
No, he uses the term twice, which is really bad. But now he's using it in the reverse sense, that somehow we're going to do the particle theory again.
Provided by observations of so-called Compton scattering, discovered by Arthur Compton. He found that if an electron at rest is illuminated by high-frequency light, the electron scatters off in some direction, carrying kinetic energy and momentum, while the light is scattered off in another direction and with a longer wavelength. Using the photon concept, the longer wavelength implies the scattered photon has lost energy and momentum.
So this is just kind of an obvious equation, right? But the point would be is that often photons don't scatter, they push the electron forward in one direction. So the scatter just has to do with how the reflections take place when you have that equal but opposite reaction that might not be completely equal and opposite reactions. So you're talking about vectors. But really, it's just kind of obvious, right? I mean, that it's obvious that it's just momentum in, and then you're going to redistribute the momentum out, And part of the momentum is going to be realized in the sense of what's the distance between the bits of energy. The bullets is one way of changing the momentum, delaying them.
These are found to be precisely the energy and momentum transferred to the electron. Thus, a photon can be considered to literally bounce off an electron, analogous to a collision between two billiard balls.
So, now that we should put that in the context of the universe expanding in redshift, and we should maybe understand that, well, if Compton scattering causes photons to lose energy in terms of frequency, then maybe that's why the universe looks red at a distance, because all the photons have gone through a bunch of scattering before they got here.
There is rock-solid evidence that light is neither a classical wave nor a classical particle.
There's rock-solid evidence that you can make something look like a wave with particles, but you really can't make a wave look like a particle.
But has both wave-like and particle-like properties simultaneously. This wave-particle duality represents, in Richard Feynman's words, the wonderfully different behavior of things on very small scales.
Blah, blah, blah. It's not really any reason to believe it's any in any way substantially different. There's force in the universe moving the speed of light, and seems quite obvious the force is telling the matter where it's going to be, and every piece of matter never goes anywhere without being forced there, and that's how the universe works. Matter is forced to move, and forces move differently depending on where the matter is.
A behavior that is unlike anything we have direct experience with. Yet,
yes, no, it doesn't have anything to do with breaking any common sense or breaking any logic or being obliged to believe in any woo. We don't have to accept the god of quantum here.
Which countless experiments tell us is simply how nature is. As compelling as this new picture may be, it is also quite unsettling.
Yeah, it's silly. That's what it is. And it always seems silly, and now I can prove it's silly, and it just isn't going to matter to anybody, because smart people are more silly than they are smart.
In the next video, we'll see that wave-particle duality undermines classical views of determinism and causality.
Yes, it undermines reasoning, and you might as well just become a religion. You might as well call yourself a religion. You might as well start wearing your religious uniforms, and, you know, you're just a Borg of religion.
And of our ability to, in principle, determine physical quantities with arbitrary precision.
I don't even know. That never made sense to me. Arbitrary precision. It doesn't even make sense. How do you have arbitrary precision? Precision has to not be arbitrary. It has to be precise, in the sense you have to create it through precision. You can't get to precision without taking precise roads. The road to precision is made of roads precision paved. Alright, enough of video and such. Ugh. Alright. So, this has been a DraftScience video presentation. Yeah, I do like that. Do a little bit of this. Yeah, do a little bit of this. Oh, look at that. Half of me is over there. That's pretty cool. Yeah, I like that. Oh, I have to remember that. I can put myself right on the corner. Ooh. Yeah. I wonder if I can get this to stay as the screen. Yeah, that would be pretty cool. I like that. Yes. I have to try to figure out how to do that. That'll be another project. I have way too many projects, actually. So, till the next time and such and so forth and whatnot. A little end. So, see you next time and such. Yeah. Hit the button, Gary.